Today I want to talk to you about something that I've been doing since 1960. Today I'm going to break the news on bad. Boost air density is what I'm talking about. I've been boosting engines since 1960, the first one being a blown Buick that went in a boat, nailhead Buick. And people have been using, since the beginning of time, a thing called a boost gauge. But the boost gauge is seriously flawed. And people who really know a lot about boosted engines compare their prowess or their engine's potential by citing boost gauge numbers. Well, I'm here to kill the boost gauge. All induction is forced. What do I mean by that? Well, here we are at the bottom of the intake stroke. At 9,000 RPM, how long do you think it took that piston to get from the top to the bottom of the bore? In thousandths of a second. Anybody got even a rough guess on that? It took about 5 milliseconds, 5 thousandths of a second. That includes all the intake valve event. In other words, not just 180 degrees, just a half rev on the intake stroke, but the valve opening point, which was before the stroke began, and the valve closing point, which is after the stroke ends. So you've got this extremely fast movement of the piston forming almost a perfect vacuum in the cylinder. So if you look at this, down at the bottom there, I've got absolute zero pressure. And right above that, I've got the pressure in cylinder during the intake stroke. And then I've got 3 map values. One is closed throttle, you're idling. That'd be the map at idle. And even there, you've got enough pressure in the intake manifold after the throttle to force idle air mass into the cylinder. And I mean, that's probably, I talk positive numbers, so let's talk in pounds since you guys use pounds of boost. I started out using inches of mercury, but I'm going to hold it all to pounds today. So you've got about, at idle, with a mild cam, you've probably got about 5 pounds of pressure in the intake manifold. On a standard day, ambient pressure, sea level, would be about 14.7, and boosted engines can be almost anywhere. I wanted to show you this first because the true arbiter, the true thing you should be talking about is not boost, it's map. If you want to talk about pressure with a supercharged engine or a naturally aspirated engine in the intake manifold, that's what drives the charge into the cylinder, that pressure in the intake manifold, then you ought to look at it like this. So we're still reading map at idle. It's pretty damn close to pushing you all the way down to absolute zero pressure. Everybody with me on this? Am I losing anybody? Ambient pressure, the force is greater. You make more power. And a boosted engine, force is even greater. You notice there at the upper right, under the boosted engine pressure level, it says boost gauge equals incomplete information. Do you see why? The boost gauge never includes the ambient pressure, but that's part of the charging pressure of the cylinder. So stop talking boost and start talking map. What's being forced is the air density. In other words, the map pressure is forcing the air density in the intake manifold around the valve and into the cylinder. And air density is not just a function of pressure. It's a function of temperature, pressure, and humidity. All 3 play into calculating air density. To give you an idea, way back in the day, the guys around Detroit decided our standard gross horsepower test is going to be normalized to or corrected to 60 degrees Fahrenheit 29.92 inches of mercury, or 14.7 pounds absolute pressure. And that gives you a density with 0% humidity of 0.07635 pounds per cubic foot. That's kind of hard number to deal with, so I state it this way. The ambient air density under those conditions, which I call AD, ambient air density, AD, is 76.4 pounds per 1,000 cubic feet. Well, engines are CFM devices, are they not? So anytime the conditions occur, and they don't always have to be the 60 and the 14.7 and the 0% humidity, but anytime those conditions occur, I consider that to be on a J607 standard day. There are other standards, by the way. This is one that even NASCAR is still using. You've got 76.4 pounds of air per 1,000 cubic feet. You mix pounds of air with pounds of fuel. You don't mix CFM. You don't mix a boost number. It's pounds of air with pounds of fuel. That gives you the air-fuel ratio, and the air-fuel ratio is pretty sacred. You don't want to get too far off the air-fuel ratio value. Here's some ways that you could get that 76.4 pounds, the first one being to specification, the other one altitude. Temperature is now at 30 degrees Fahrenheit. The pressure is lower, but we still have 76.4 pounds per 1,000. We still have a 100% day. Now, when I say 100% day, dyno correction factors correct you back to that value. So everybody in the world can compare what their engine would have done had it been under those conditions on that standard day. So it doesn't have to be exactly 60 and 14.7 and 0% humidity. In the third column over, I've got the humidity at 100%. Temperature's down a little and pressure standard, we're still at 76.4. The engine cares about the air mass. It really doesn't care about those other numbers. It cares about the air mass, because without the air mass, you don't burn the fuel mass, and you don't make the power number. All the examples I'm going to give you today, I've kind of standardized. The engine's running at a 12-to-1 air-fuel ratio, and the brake spec is 500. So doing the math, the brake-specific air consumption is 6 pounds per horsepower hour. 100 horsepower would therefore require 600 pounds of air per hour, or at 100 horsepower for a minute, 10 pounds of air per minute. So I need 10 pounds of air per minute to make 100 horsepower with gasoline at a 12-to-1 with a 500 brake spec. So if 1,000 cubic feet of air equals 76.4 pounds, then 131 cubic feet per minute equals 10 pounds per minute equals 100 horsepower. Everybody with me? Cool. Let me tie it together. Engines pump CFM, and I'm not talking about CFM in this room. I'm not talking about ambient CFM. I'm talking about engine CFM. CFM engine is different than CFM inducted. That's a powerful thing to realize, because guys always talk about the size of the carburetor and how many CFM, and et cetera, et cetera. There's two different values here. The density of the CFM that you're inducting, that the engine processes, is directly related to the horsepower output. Engines pump their own displacement every 2 revs. That's because you only have one induction per 2 revs. At any fixed RPM, the engine CFM pumped is constant. The throttle doesn't control the engine CFM. The throttle controls the manifold air density. Intake manifold air density. That's what the engine inducts. And that's what's highly important here, MAD. manifold air density. Throttles, cold air scoops, superchargers, turbochargers, and intercoolers are all density machines. They either increase or decrease the manifold air density of the engine being pumped, the CFM, engine CFM being pumped. If you couldn't reduce the manifold air density with something like a throttle, the engine would never idle. The mass flow would be too high. Now, diesels are a different matter. They throttle on fuel. Today, I'm talking about gasoline. If you think I'm just a diesel guy, you're sadly mistaken. I'm a turbo guy. Turbo don't care. It can go anywhere. So why is manifold air density so important? An engine's air-fuel ratio is measured in mass units. It takes pounds of air, not pounds of boost, to burn pounds of fuel. I might be repeating myself. I'm just trying to really burn it in. So MAD times the CFM pumped determines your engine's power output. And MAD can be displayed as mass per unit volume, in other words, pounds per 1,000 cubic feet, I like, or percent of standard day. I really prefer percent, and you'll see why in a few minutes here. MAD readings apply to any internal combustion engine, spark or compression ignition, blown or unblown, any fuel. MAD readings can be compared at any altitude, anywhere on the planet. Now you have a common language, which boost is not a common language, and it cannot be compared anywhere on the planet because it doesn't account for the changes in ambient pressure. So here's some base conditions for the rest of the talk. The volumetric efficiency is 100%. Thermal losses are constant. Frictional losses are constant. Viscous losses are constant. And all power numbers are observed. Now, guys talk about corrected horsepower. But if you're in Denver versus San Diego, California, you're down on power. But that's the power you've got. If you're going racing, that's all God's given you if you're naturally aspirated. And it kind of compromises you a bit even if you're blown. So I want to take you back to how this all started to occur to me. 1960, El Mirage Dry Lake. I was real high tech with my 65-buck Studebaker and my Dickies fire suit dumped in the borate solution in the 55-gallon drum. I even fireproofed my tennies with that. It's very scratchy. And these were my instruments. A moon density gauge. Guys still use these to, I think Intercomp makes a current version of this. Tuning your naturally aspirated engine, the ambient air density, if you kept a book, you jetted your Holly or you pilled your Hillborn. The engine that I had run at the Champion Dyno in Long Beach, where I had conditions very much like 60 degrees F and 14.7, I had a 580 horse Hillborn injected small block in that Studebaker. Car looks like hell, but the engine was beautiful. Running in Long Beach, 14.7, 60 degrees, altitude virtually zero, 100% manifold air density, 580 horsepower, standard day, no power loss. Then I went up to El Mirage. I didn't have this instrument, by the way. I had the old ones I just showed you, and I was doing the math on a piece of paper. I wish I had this back then. But you see what's happened. We're still 60 degrees. In this, I'm going to keep the temperature constant so you can just look at the rest of this. I'll have some temperature examples later, but basically you're at 2,800, a little over 2,800 feet of altitude, and I'm down on power. I'm at 90%. manifold air density, which knocks about 10% of your power off. Manifold air density and power are directly related. So I'm at El Mirage. I've been on the dyno down in Long Beach. 12-to-1 was my favorite color on the plug, and it wasn't there. It was a lot darker. So I leaned out the Hillborns, and it cost me 56 horsepower. Then I went to Bonneville. This is really disheartening because I wanted to get in the 2 club badly. And I thought at 580 horsepower, the Studebaker would go fast enough to get me in the 2 club. But here I am. I'm down to 86% on the density. I got 5 miles of beautiful white, 4 feet deep at the time. But my power is down 14%. I had no ram air. I was basically inhaling underhood air, which is another no-no. If you care about density, you don't run an exposed air filter element under the hood ever, ever. I've seen some beautiful stuff at the SEMA show 2 years ago where a guy had a blower, had like a open element air filter that wrapped around right over the headers. Well, if you're in it for air density, and that's what you should be in it for, you don't induct hot air and then make it hotter in the blower and then intercool it. You're just giving away 30, 40 horsepower by doing such stupid thing. So here we are, we're at 4,200 feet, and I decided, okay, I'm going to put an air scoop on the Studebaker, have Earl Scheib paint it for $29.95, and I built an aluminum box. It came down, and the injector stacks went into the box, and it sealed around the stacks. So I had a positive pressure now, and I picked up 24 horsepower. Well, what happened was I picked up 0.6 of a pound of pressure over ambient at 190 miles an hour. Now I'm back to 522. So, which, oh, by the way, is where I was at the lakes, at a lower altitude. So this ram air thing, as long as it's cold ram air, this ram air thing really works. But nonetheless, there was no 2 club for me. I went 189, and I was really, really, really looking for how the hell do I improve the manifold air density in this Chevy. Pitted next to me at Bonneville. Oh, you know Geisler. Bruce Geisler and I have run together on and off for 51 years. And he's absolutely crazy and the coolest guy on earth. Anyhow, his T-shirt, and nobody tell Geisler this, but his T-shirt set up my entire career. I would rather be blown than injected. And then I thought about the answers at Pikes Peak. And you start to look at where that goes. Here's the same engine at the start at 9,390 feet. Your manifold air density is 71% of standard day. And the power is now down to 413, but let's take it to the top at 14,110. Density is down to 60%. Power is down to 348 horsepower. Anybody who runs naturally aspirated at Pikes Peak, this should be really depressing, I would think, especially if you dynoed your engine in Long Beach, California. So the power losses reflect the drop in manifold air density. Now, I wanted to add this little thing because the power losses will be greater because the parasitics don't drop, the frictional, viscous, etc. You got a bigger heat sink relative to the BTUs you're producing. The power losses will actually be greater than what I showed you. Similarly, if you increase power, the power losses will be greater than what I show you because the frictional and viscous really doesn't increase, but the power does. So parasitic versus is what I'm talking about. So unblown engines, how can I use a MAD reading? What do I do with it? Well, you saw the intake air location and intake air ducting thing I did with the Studebaker. Air filter restriction, you can perfectly size a carburetor with this setup, or the throttle itself. You look at a guy running a cup car with a plate. Plates are worth about 400 horsepower, but the throttles remain the same size above the plate. Anybody ever driven a plate car? Let me tell you, about the last third of the throttle is dead because the plate's throttling now. Your butterfly area has exceeded the restriction of the plate. So those guys have to plan everything in advance and build momentum and what have you. It's like racing Formula V road race. I mean, everybody's got the same power virtually. I'd go nuts driving a plate car. So throttle size versus engine requirement. A lot of guys run big mother throttles. You tip in. You get too much air real quick. It's not real streetable, but it's really badass to have a 4-inch throttle. So guys do that. Most of the throttling takes place in about the first 30 degrees of movement of the throttle blade. Once you get enough throttle area, now you're throttling on the ports or the cylinder heads. So one last thing I put here under unblown engines is charge air cooling. I call it poor man's forced induction. Now, I'll give you a couple of examples. I've done a number of these. We ran a car called the Sundowner in 1979 at Bonneville. I was going to turbo, but I ran out of time. So I left the intercooler in place, put a set of headers on it, changed the compression ratio in the cam, and built a box around the carburetor. And I used liquid CO2 to chill the heat exchangers. So the car ran a 211 on a single 4-barrel at 4,200 feet of altitude, unblown. Not bad. I mean, at the time, the fastest single 4-barrel Corvette was 186 miles an hour, and that was at sea level. What did I do with that? I increased the manifold air density by cooling the air. This is the underhood of a project I did with John Rock at GMC called the Cyclone. Convinced him to set a record at Bonneville with a truck. Here we used ice water to cool 2 heat exchangers, one on either side of the radiator. Ram air came through the grill into the ducting and through 2 heat exchangers chilled with ice water. So on a 110-degree day, our intake air temperature was 51 degrees. That's a pretty significant, almost a 6% increase in power. Of course, a little ram air value went along with that. Now let's get into turbocharging a little bit here. Turbocharging is something that I've been doing now for, well, since 1967. Is that 50 years? This is my first speed shop, retail shop in San Gabriel in 1967. And the first turbo engine I did is in this hydroplane called the Nailer. And it's intercooled, but with a very crude charge air cooler, water jacketed or water cooled charge air cooler. It made enough power to push the rudder out of the water. In other words, hydros run on the prop, the tail gets up. It pushed the tail so high we went sideways, which put it, next thing I just told Rocky, the guy who owned the boat, put it on the trailer, I'm going home. You've got to get a longer rudder. I was infected, I should say, by the Corvair Spider, and Hugh McInnes, who was the chief engineer of TRW Turbocharging at the time, became a friend of mine. And why turbos? Well, mad. Decision is easy. Do I do this or this? So I kind of chose the turbocharging. By the way, the IMSA Monza was Al Holbert's, and we took it from 580 horsepower with a big engine down to a 5-liter engine at 930. Kind of overwhelmed everything about that Monza. And in fact, we went so fast that the chin spoiler folded under and we ran over it. A lot of downforce. So let me run through some various types of supercharging and show you how this measurement of a MAD becomes very, very, very crucial. Here's a Roots blower, 871, 671, 1271, you name it. They're about 45% efficient. That means they heat the air quite a bit. Here the 60-degree air at 20 pounds of boost, manifold air temperature, is 381 degrees Fahrenheit. Your density is up 46%, a 146 at 20 pounds of boost. Now we go to a screw-type supercharger, 65% efficient. Oh, by the way, the horsepower was 846 at 20 pounds of boost. Now we're at 959 horsepower. We're still at 20 pounds of boost, but we're running at 282 degrees in the manifold, and our density is 165. Now we go to a centrifugal, which I call a belt-driven turbocharger, or a turbo, which is run-off exhaust pressure. And our efficiency is up to 76%. Our horsepower is now 1,003. We're still at 20 pounds of boost on this engine. Our manifold air temperature is 250. You starting to follow? We're just evaluating all these different blowers. You can use this to evaluate one blower and its overdrive, let's say. We had a case where a guy changed the pulley on a blown late model Camaro to pulley up and get some more boost, and he actually went slower. That's because his boost number went up, but the temperature went up to an even greater value, decreasing the MAD. Everybody on board? All right. So this is one hell of not only an evaluation of equipment. You run this thing, you might know more than the guy who actually sold you the blower about his blower. And here is 100% efficient. It's an adiabatic process. It means no heat leaves or enters the system. It's impossible for a blower or a turbo or any compressor to be this efficient because you're doing work to the air to compress it, and that puts heat into the air. There's no getting around it. But here, the horsepower would be 1,070, and the manifold air temperature would be 205. There's no intercooler here, of course. So this is pie in the sky. I just thought I'd throw it in there just to tell you we started at 60-degree air, and we're at 205 with a perfect compressor. So what changes air density? Well, if you increase the pressure, air density goes up. If you increase the temperature, air density goes down. If you increase the humidity, air density goes down. Not a lot. Humidity has a very narrow window of change. So we've covered increasing manifold air pressure. Now let's look at reducing manifold air temperature. When we talk about turbochargers and intercoolers, I'm going to use a 76% efficient compressor. I'm going to use on our air-to-air intercooler with 60-degree cooling air, 82% effective. And on ice water, 90% effective, and it'll be 33-degree water cooling the core. Once again, our naturally aspirated setup is at 580 horsepower, 100% MAD. Now we go to 20 pounds of boost. No intercooling. We're at 1,003. You might remember that number. I'm going to give you some examples of projects I've done through the years real quick. with no intercooling. First turbo Buick ever, the 76 Indy pace car. I was directly involved at Buick on that. That's their first turbo ever at Buick. They discontinued the V8 because of the fuel crunch and were stuck with a V6, and the USAC guys laughed them out of the speedway, told them, go home, and the Roadsters are going to run over you. You'll never make it to the pits. So we did this with Buick. We did the first, we kind of infected Europe a little bit too. Volvo hired us to do a turbo version of their B21 red block. This is mid-70s. And this was the first O2 sensing fuel-injected turbo engine ever done on the planet. That was for Volvo. They came out with their production turbo version of this in 1980. It's hurry around Hondo. This is a Hilborn injected setup with two blowers that were being used at the Speedway at the time on the Offenhausers. 1,800 horsepower methanol engine and an 18-foot boat. We were national champion, and all the guys with blowers left the class, and the next year we had no class to run in APBA. The compressor efficiency being the major difference. We did a prototype V6 marine engine, no turbo, with Chevy. We built the Grand National concept with Buick, the gray car in the background, and the guy looking at me, getting ready to tell me another lie is Junior Johnson. I'm telling you, what a sweetheart he is. I just got some of his blueberry shine. Really good stuff. Anyhow, that was a 3.8 at 454 horsepower. We did water methanol injected. And the production Buicks were all single turbo. The first diesel pickup turbo kit, this would be 1981. We had been working with a 6.2 diesel as a marine engine starting in 1978. And finally they came out in the pickup trucks in late 81, the 82-year model. This is the first product of the diesel aftermarket. This is a seminal product of the diesel aftermarket. Tuner cars. When there was no such a term anywhere in the world, we built tuner cars. We didn't know what they were tuner cars, but they are now. We twin turboed the small block Chevy. This also used water methanol injection. And had the first car ever driven on the street by any magazine over 200 miles an hour, June of '84. The prior fastest car was 163, so we got them by 41 miles an hour. I sold these cars throughout the 80s through a company I formed called American Turbo Car Corporation, which we're bringing back. We also did some turbocharging in NHRA, Top Fuel, and Funny Car, and talked to Wally Parks and Graham Light about this stuff, and sat in Wally's office with Graham there, and I told Wally I wanted to be the first Top Fuel car to go 300, and he told me it wasn't going to happen because nobody knew jack about turbocharging in the middle of the 80s, so it never happened. But we remained friends, and Graham Light, of course, is still with us. I'll be seeing him next month. That was Prudhomme's last funny car. We tried to get chassis that worked. That was Gary Beck's top qualifying car, bought it from Larry Miner, 1986 Winter National. So I had a car I knew worked, and I did a flat crank late model Hemi with a lot of turbocharging gear and a lot of very monster-looking aerodynamic drag for the engine. The Cyclone was a project I did with GMC. I originally intended it to be a big block twin turbo in a short bed half-ton, and in a meeting at GM, Chevy took it from us and did the SS 454 or 454 SS, which was a 230 horsepower pig, and went 87 miles an hour top speed. This is the last the kind of non-intercooled setup. I just wanted to point out the ram air above the back of the body there. The inlet area on that thing was quite a debate because the car ran best mile, I think, was 432. And of course, this car's been retired for, nearly 15 years. But for 2 decades, it was the fastest piston engine, wheel-driven car on the planet. The inlet area on that thing looks awfully small. There's a 1271 in there. And, we ran Chryslers of various sizes for various classes. But we put an air density setup on the feed to that GMC blower and found we were up in the air density about 8% above ambient. So it was working perfectly. And this may be the last one. This is a little diesel we ran back in the 08, 09. Car number, by the way, is 777. Our record was 777. We put it in the NHRA museum for a few years. Pulled it out, went to the Nationals at Topeka, won the Nationals. We turned to 777 in the final round. I should be a gambler. That's all I got to say. Oh, and Paul Dallenbach, Pikes Peak, he ran naturally aspirated. Wally, his dad, is a friend, and Paul is a wicked hill climb driver. Well, probably Reese Millen and Paul are right up there. This was a 400, 500 horse small block. We did a 440-inch SB2 and twin turboed on alcohol. We made 1,402 horsepower. Completely changed the car so badly that at the start the first year, he twisted the half shaft off on one side of the car, leaving hard from the starting line, and we were the top qualifier. But turbocharging heals up the depression of naturally aspirated at Pikes Peak. We're also doing a top dragster, which will be running blown and then ultimately super turboed. This is another currently non-intercooled setup. What I do on these non-intercooled engines, a lot of them, is run nitrous as a cooling agent. And of course, you know, it adds horsepower. Done right, it's a pretty wicked combination with turbocharging or supercharging, diesel, gasoline, whatever. It's just modulating the nitrous is kind of refined. That'll be the dragster, and then the zoomies will go away. We're just getting the 60-foot worked out. The zoomies will go away, and there'll be 2 turbos blowing the blower. And here's our current version of the non-intercooled V8 that we first did 50 years ago, thereabouts. So let's look at different types of intercooling. Here we are at sea level, J607 standard day. We're turbocharged. I think what I'm going to do here is probably change elevation again. We're at 1285 at sea level with intercooling. Here's a number of air-to-air intercooled projects that we've done. Diesel that we drove to Bonneville, and then on a power tour and a bunch of other stuff. This is still a 2002 record, which we still hold at I think the two-way is like 217. Another intercooled diesel. Air-to-air intercooled road racer. This is a super turbo 14-liter. I ran with Mike Ryan at Pikes Peak. Intercooler in the front, and one thing we did there is we misted the face of the intercooler with water, because as you get up in altitude, the air density is so low, you don't have a lot of density to reject the heat to. So latent heat of vaporization of the water really fix that. It's a beautiful thing. I just took one of my water meth systems and some nozzles and fogged the intercooler. With 2 stages, you know, it's a screw blower blowing a very large turbocharger. So it comes off the turns real hard, minimum smoke, maximum fuel use in the engine. The thing that, leveraging density, Joint Special Operations Command, we've been doing military engines for 40 years. The first ones were Marine engines for the SEALs. The guys were having issues with the Humvees at 14,000 feet in Afghanistan, and that was a Frag 5 like the one I'm sitting on. They're pretty heavy. They weigh about 14,000 pounds with nothing in them. And they had about 52 horsepower at the ground at that altitude. So they've got 190 flywheel, about 113, 114 to the ground at sea level. Humvees are drastically underpowered. Then they double the weight. So these guys were in the field of fire too long. They couldn't get to the fight quick enough, and they sure as hell couldn't get the hell out of Dodge quick enough. That's why I went to Pikes Peak, to figure out density management of the turbocharging at altitude. We also, this is something, I'm just showing you guys this because I'm feeling real patriotic. You realize that it's about 8:30 in Pearl Harbor right now on the morning of December 7th. I've got this real serious patriotism thing going on. After an 8-year battle with all the defense companies and all the diesel engine manufacturers in the United States, Oshkosh Truck, with our diesel power, we supply the engines for this JLTV, what I call the Jolt. It replaces the Humvee. And we'll be doing them through 2040, which is a hot rodder's dream come true. It truly is. I wish I was younger. By the way, Pearl Harbor is 75 years ago, and I'm 75. It's kind of a weird vibe I've got going on today. At any rate, here's another one that's air-to-air intercooled. By the way, this thing has 18 inches of suspension travel. It is a military trophy truck. It goes through open country twice as fast on the same course as the prior vehicle, prior gold standard, which was also an Oshkosh vehicle. So quite a piece. We beat every defense manufacturer. It took us 8 years, quite a contest. Air to ice water. This is one of my favorites. We first did this a very long time ago. You know, it was I'll give you some examples. The intercooler is a V-shaped guy with two elements on top of this, my first Marine twin turbo engine. These things are incredibly effective. They cut the temperature, water temperature versus boost temperature by 92%. That's called effectiveness. Here's the first, to my knowledge, use of a water-coupled intercooler in a road-driven vehicle. Basically, in the Monza, this would be in 75 or 76, I used marine intercooling and a second set of heat exchangers, which you will find on the new 6.7 Ford. And we did it on the production Cyclones as well. Geissler Studebaker. We took the road race engine out of the Monza, put it in the Studebaker, and it ran 217 at Bonneville, which made it the world's fastest passenger car back in '79. This is an 850 horse marine engine. Became the standard of the world. These were sold all over the world for 20 years. Then we started this series. This is ice water. So you've got this ice water tank, which is a Coleman ice chest with a rubber duck floating inside. And later there was 2 rubber ducks, and they had children in there. Here you see the marine intercooler once again in front of the plenum, and we're blowing 2 Holley carburetors, pressurizing 2 carburetors. Way back then, the fuel mass required wasn't available from any of the fuel injection companies at the time. This would be 1980. We did a street-driven version in a Firebird, shipped it to Johannesburg, South Africa. Customer's name was Peter Manilis. He wanted the fastest car in South Africa. So at 6,200 feet of altitude, it ran 252. And he drove it on the street and has driven it on the street ever since. Tried to sell it back to me recently. So that's one of the American turbo cars, probably the fastest one we ever did. Viron, when they first came out, ran a similar number. There you see the Coleman ice chest over there on the right side. We started really working with the Firebirds, ran a 67, and then we ran a best mile of 83, in 87. Much more intercooling is the point here. We doubled up on the intercooling and went to Dominator carburetors and got more manifold air density and picked up some speed. Same car, I just painted it red. Offshore racing, we were real successful around the world with turbocharging until APBA banned turbocharging in offshore racing for 25 years. So it's back now. You can now turbo them again, but they got rid of us. This is our, I'm just going to show you some late stuff we're doing here. This is will be our 2017 Marine Duramax based on the new L5P. We're also doing a super turbo version of it for the Navy, for the twin engine, various other things. We're real happy to get rid of the Somali pirates with Banks Power. And we're going to go after the diesel land speed record, which is 350, probably 2018. This car has been 382 with a 53 DeSoto iron motor, turning 8,800 RPM under a 1271 with a dose of nitro. It's been 382. So that's about 1,200 horsepower, and we're way over that with the Duramax engines. It's just got to sustain it the 5 miles down and the 5 miles back is all. But it's a hot rod. It's 2-wheel drive, Yankee iron, nothing fancy. The English did it with 2 engines, 4-wheel drive, and $13 million worth of effort. That's your number. My number is 17 million. But whatever they spent, I'm going to spend about 150 grand. And that's probably on the high side. One last thing, and this is an answer thing. What if they had air-to-air intercooling and a turboed engine and went up Pikes Peak? So we start at 1,285 horsepower at sea level, and go to Bonneville. We've still got 1199. Still, by the way, still all 20 pounds of boost. Everybody getting the drift on the boost gauge doesn't mean a damn thing. It's some nebulous number that's out there. All of these examples are 20 pounds of boost. And the power's all over the place. So then you go to the starting line, we're at 1,109. And at the top of the mountain, we're at 1,037. So we've got basically a 22% loss in power at the top of the mountain versus 40% loss in power for the naturally aspirated. So there is some altitude compensation inherent in supercharging or turbocharging and going to altitude. So basically, the factors that determine the power output of the engine are the manifold air density and the engine CFM pumped. Now, if you want to up the engine CFM pumped, you can turn the engine faster, make it bigger, or make the heads work better. All of which will give you more throughput from the manifold. The last one will give you more throughput from the manifold to the in-cylinder density. So what I've got is this little thing called the iDash, which allows you, I've been showing you a screen on the damn thing. We also do a 2-inch version that goes in a gauge hole. It allows you to monitor, evaluate, and refine the supercharger density gain, the supercharger size and overdrive, the turbocharger density gain, the turbocharger size, any compressor mods, trick billet wheels, Batmo wheels, or whatever the heck screaming things these kids do. Are they better or are they worse or are they just loud? Ducting density loss, which is a biggie, can be measured with this setup. Intercooler heat absorption rate has to do with the mass of the intercooler. You know, if you're doing a drag race thing, the intercooler, you got to heat the intercooler first. It's transferring heat to the air or to the water all the time, but you got to heat all that aluminum. So when you come out of the hole, you know, instantaneously you got a lot of BTUs. That decays down as you heat the intercooler itself. Then it normalizes and your heat rejection flatlines. You with me? If you got a lot of intercooler, I don't mean a thick air-to-air, because you get too thick, they block airflow through them and they're worse. But you can find all of that just by watching density gain across the intercooler at the same speed and load dyno wherever. Intercooler density gain, of course, and intercooler coolant flow rate. A lot of guys are using water-to-air intercoolers, and they're running a bilge pump, making about 12 gallons per minute when they need 70 gallons per minute. So in that road race car, I was running 70, 80 gallons a minute with a belt-driven centrifugal water pump. Anyhow, here's the bad part of it. Manifold air density minus ambient air density gives you the boost air density. This is what your charging system is doing. It's the only true evaluation of a boosting system. Ambient air density plus boost air density equals manifold air density, and that is the key indicator to the power output. It's not as good as a dynamometer, of course, but when you're out racing, the dynamometer isn't there with you. And you can compare manifold air density or boost air density gain with any other guy in any other engine shop or any guy you're racing anywhere on the planet at any altitude. It is the universal comparative term for engine power output. It's kind of like a batting average, the way I look at it. If you're under 100, like going up Pikes Peak, naturally aspirated, you are truly a victim of Mother Nature. 100 to 200, especially get up around 200 on a street machine, you're getting with the program. 200 to 300, people are starting to avoid you. No, I'm not racing you. 300 to 500, you're the master of the universe. The boost gauge is dead to me. All right, guys. Thank you very much. It's been a pleasure.
Thank you. Thank you.
Hey, great presentation, Gail. What about on the exhaust side on a turbo? Because now all our customers are spending all this time on the compressor side, but they're avoiding the turbine side to see how much back pressure they're running. Is there anything like what you're doing with your manifold gauge that you can put on the exhaust side?
Yeah, in fact, I'm just finishing, I'm trying to do it with a single sensor that'll take exhaust drive pressure and temperature at the same time.
Okay.
I kind of look at it this way. You want to minimize that. Turbine development, turbocharger response is a function of turbine size and total flow capacity. A lot of guys drag racing will run a little tiny turbine. The theory is it gets a turbocharger going quicker. A good way to monitor whether that's correct or not is be logging manifold air density and see how quickly it rises. This whole thing, I didn't mention that my little meter, my little gauge, and that little 5-inch thing has a SD card slot for logging.
So you're recording it, yes.
Yeah, so you can just pop it in there and get whatever you want to get. The whole deal with drive pressure is you soon pay the piper. If the turbine is small, you older guys will recognize this. I call it the May West turbocharger. Kind of small on the bottom and big on the top. Who's a better, more modern example of that? I gotta up my game a little. So the whole deal is you soon turn into boost pressure dropping literally and turbine inlet pressure doing this. Right. I don't want to ever hit that crossover point if I can avoid it. I always like to have the turbine inlet pressure lower than the boost pressure. We're just talking pressure comparison here. So nuancing the turbocharger and nuancing the intercooler and how it matches to the situation, this tool is so damn good at that. Even getting into Billy country and looking at the valve timing.
No, absolutely.
There's so much that can be done with this. And frankly, if you had a belt-driven supercharger at wide open throttle and you perfect the cam so the head works better, the manifold pressure will drop, right. Literally.
Oh, absolutely.
Yeah.
Thank you so much. Hopefully the temperature will drop enough that that the boost gauge, if you were going to use one of those, but we're dead, would drop actually more than
initial temperature. We've got this octane limit. That initial temperature has a big bearing on how much you can drive the manifold density up. I mean, if we bring that temp down, I'm talking about detonation threshold.
Right.
You run on C or whatever it is, 116, whatever the racers. But I do a lot of street stuff, and you always have that octane limit. So getting that initial temperature down while keeping the density up is a big deal. Processing it through with proper valve timing, and not processing it all the way into the exhaust manifold. You don't want to put...
Shortcut, right.
Yeah, you don't want to put air fuel in the exhaust manifold.
Thank you so much. I really do.
All right.
Hi, you mentioned that you don't want to go over on the intercooler thickness beyond its ability to flow through it because then it becomes counterproductive. Have you done any studies or found a core thickness that beyond it, which is unreasonable to have? 5, 6, 7 inches, and does it depend on the application?
Yeah, if it's a low velocity like a truck, I had a guy from Texas call me the other day, how thick's your intercooler for my truck? I said, 3 1/4, something like that. I don't know, not thick enough. I want 4 inches or better. Most 4-inch core material, regardless of the fin count, is too restrictive, so your radiator behind it can't reject as much heat. The engine gets to overtemp before you get to the power gain. Literally, the engine will pull out fuel to save itself on modern ones where they have EGT being measured constantly. It'll derate. In other words, the intercooler is absolutely only good for conversation. It sure as hell isn't good for density or power. So how thick? It depends on but at about 3.5 inches, if you drop the fin density to where the air will go through properly and do the rest of the cooling pack, it's not rejecting enough heat anymore. In other words, you don't have enough fin surface area anymore. There's kind of a balancing act.
Makes sense. Thank you.
All right.
Yeah.
Yes, sir.
You ever looked at the compressed air supercharging system?
The which?
Compressed air supercharging system?
Compressed air supercharging? Did a project years ago with Mickey Thompson.
Right, but somebody has finally figured out how to valve it.
Yeah, the issue.
They're building a unit for drag racing.
Well, there was 2 different things there. This was kind of a flopper Mustang, and the valving was part of it, and the total capacity. In other words, if you really want to have enough air to make the pass, enough pounds of air.
Right.
Of course, we weren't running as quick as we do now, way back then, but the valving was first an issue, and then the valving issue was resolved, and then the tank capacity became an issue.
Right.
So.
Well,
Then he tried oxygen cylinders.
Yeah, yeah. Scuba tanks now hold 3 times as much air as what you guys had.
Yeah,
back in the 60s.
you know, how many pounds of air are in the tank? It's, you know, what I'm saying. So if you've got enough air mass in the tank, you could easily do it.
Yeah.
You pay a weight penalty, but there's no blower or anything.
Wait a
so
minute, you're taking
maybe
the
it kind of
blower
levels
off,
out.
you know?
Yeah.
Plus the air temperature coming out of the scuba tanks is way below 0. And you know,
Yeah.
if you go to Bonneville with a diesel liner, they're just going to ship that thing back over from England and put it in high gear and take it away from you.
I hope so. Nothing, you know, it's like our little Cummins-powered pickup truck. I'm still waiting for somebody to, you know, guys go, why don't you go back and go faster? And it's, why go race yourself?
Well, I'm still waiting for you to go to Bonneville with your diesel streamliner because you told me I was on a crew.
You are going to crew. You're screwed now. I got witnesses. I'm shooting for 2018 on that. Do the dragster first. Anyone else? I got a lot of answers. Some of them are correct.
Any other questions?
Anybody else got a project going? Anything? Oh, here comes a gentleman. By the way, Billy Godbold, if you're turbocharging anything, talk to Billy Godbold at CompCams.
Picking up on the compressed air injection, being a scuba diver and having scuba tanks and messing around with superchargers, I've always wanted to try shooting high velocity air out of the scuba tank through the venturi and getting the Coanda effect of drawing in a lot more air too, plus the supercooling effect of the expansion of the air coming out of the scuba tank. And I think for quarter mile racing it's got great potential, but I've never had the time to really do it.
You know what would be cool, talking to your point, is to put an air receiver on a turbocharged car and use that to launch. In other words, kick the turbo in the ass with some compressed air right through the compressor.
Yeah,
Yeah.
we'll have to try that.
I mean, there's an inventive, you know, if we were all shipwrecked on a desert island, this is a comment on racers, and you come back a year later, we'd have a high-rise hotel, we'd have a racetrack, you know what I mean? It would come out of, we make them from coconuts. Somehow it would happen. That's the beauty of doing what we do. It's all about invention, isn't it?
Anyway, thanks for a great presentation and a lot of very thought-provoking stuff too.
I hope so. Thank you. Yes, sir.
Hi, Gail. Great presentation, by the way. Very, very cool stuff. My question is, well, I guess my statement is, oftentimes I like to listen to the language that people use. And a few minutes ago when Billy asked a question about the exhaust, you used a word that's different than everybody else. Most people talk about back pressure. You called it drive pressure. And so we spend a lot of time at my place discussing the difference between the two. And obviously we have to have some amount of pressure to drive the turbine, but
Absolutely.
then if we have too much left over, we call that back pressure. So I just thought maybe I'd bait you a little bit and give you the opportunity to expound so that the people that are turbocharging could...
Well, I'll expound this way. Belt-driven, gear-driven, those are all driven by increased firing pressure. What am I saying here? Say you've got an octane limit or a structural limit for the engine. You get to a certain firing pressure and you're starting to break parts. Now, you add more to do your blower. Why do that? Why not add it on the exhaust stroke? So now all your firing pressure is available to make power at a given octane. To me, a belt-driven device hamstrings you. The only reason to use one, like the Super Turbo I was showing, is to kick it in the ass, get it going, nice big turbochargers, great for mid-range and top end. Not a lot of drive pressure required for them because you don't have that tight turbine to get it to respond from downstairs. It's more like the turbocharger match on the old Offie Indy cars. Or that Firebird at Bonneville. I'm running like 26 pounds of drive pressure and 38 pounds of boost pressure. So that type of thing. I'm a real advocate of not using a belt-driven device at all, except as an augmenter. And now we've got an electric-driven device. We first used to push the Streamliner 15, 18 years ago. It's becoming production at Borg Warner now. So we'll have 48-volt electric systems coming in our future vehicles real soon. And I can't wait because the device we're working on requires 48 volts. It pulls about, I don't know, 6 kW of energy real quick. That's a lot of amps at 12 volts. So more than the starter, about twice, 3 times the starter amperage. So there's a lot coming. I think did I answer the question though?
Close. What I was really looking
Because I tend to drift off and just...
Clearly, yeah. So the question that I was really hoping to define is if we were to put your gauge on the other side of the engine, and I could look at the relative difference between the pressure or manifold air density on one side versus the other side, that has a direct effect on the engine's performance. So what I was getting at is we encounter a lot of folks that maybe don't quite see the difference between having that huge manifold density, but as you pointed out, if I try to get there with a little tiny turbine, it doesn't necessarily help me. So I wanted you to expand on when does enough pressure in the exhaust to drive the turbine become offset by an excessive amount that I can no longer get rid of?
How do you know when you're there? If it's a drag race car, it's going to be elapsed time. We did a deal with the guys at Garrett about 10, 12 years ago using the same compressor in 2 different turbine sizes, one correct one and one that was the May West. And everybody run that T3 driver, T4 compressor thing back years ago. Well, going T4, we had better ETs. The thing literally wasn't that lazy getting on the turbocharger. So, and once on, everything else was way better. So you might suffer a little bit in the 60-foot, but oh my God, did you make it up, at the 8th and the quarter. So, instrumentation and data logging, empirically doing it is probably the quickest way for anybody.
Well, that was a good answer. You've had a great career, and we're lucky to benefit from your experience. So great presentation. We appreciate it.
Thank you. Yes, sir.
First, I'd like to thank you for coming and speaking. I thought it was a great presentation.
This will be the last question, so make it a good one.
2 things. One is when you do hit Bonneville in 2018, if you need some oil recommendations, please come talk to me. I'd love to help out with that. Just a little plug. Secondly, is I think you just kind of hit on this in your first answer to the last question. So some of the higher end racing teams I deal with, they're actually running an electric assisted turbocharger to overcome the lag. Is that what you were just talking about as far as? So we're going to see that in the near future versus they're experimenting. They're still running, like the Formula 1 teams, WEC teams, they're running it now. I was kind of curious if you're dealing with anything like that, how soon it would be till we would be able to have something like that.
Yeah, there's a little echo on this speaker, but am I dealing with electric-driven supercharging?
Correct.
Yes. Yeah. When I was talking about going to Buick and doing that pace car, a guy named Walt Ware, who was president at Garrett Air Research back in those decades, a good friend of mine, we teamed together. He sent the stuff and then called me and said, "You're going to Buick with me," because they can't figure it out. So after leaving Garrett, he worked for Roger Penske. Penske had bought or was given Detroit Diesel and some money to take it by GM. And Walt went there and helped turn around the company. And then they sold it to Daimler. And Walt was the president of a company that built electrically driven centrifugal superchargers. This is 18, 20 years ago. One of which we put in a Dodge Cummins push truck, which was lazy as hell out of the hole, and a dually, 1 ton. And suddenly we had the next year wheel spin. You know, and we're loading toolboxes in the damn thing to try to settle it down to push that streamliner. By the way, I'm an advocate of 4-wheel drive, badass push truck. That makes the 5 miles even longer, if you follow me. You're under power rather than on the push truck for more time. So you go faster. It's a very successful thing. He had them running on buses in England. He had them running on semis here. Very good deal. Unfortunately, the company wasn't financially sound and folded up. So now we have not only Borg-Warner, but a number of other, Valeo, I think is another company out of France, that are doing these electric superchargers again. And I think BMW, somebody has a production application coming like next year. To me, it's so cool I can't wait because it allows me to really sweeten up the turbo match and not have to worry about the out-of-the-hole thing as much. So it's coming. I wish they'd just get it done. We're doing 48 volt first, then we're going to do some 12 volts after. So for all the older cars, all the older applications. So just one last thing, guys. I used to teach a lot, and the last time I taught major was a 40-hour seminar at General Motors Institute on engine design and a turbo application, June of 1980, and open to graduate engineers in all companies, which was odd for GMI, but they let me do it. And I was preaching a 2-liter highly turbocharged engine because we were coming off the fuel crunch. In fact, in 79, we kind of had another little rumble. And a couple of recessions there, late 79, 80, and into 81. And so I'm preaching to these guys, why don't we do like a 1.5 liter, 2-liter engine that's little, gets you fuel economy, then you hit the loud pedal, and suddenly it's bigger and gives you the performance you're looking for. And I about got laughed out of that place because cast iron's so damn cheap, cubic inches was so damn cheap, and turbos cost as much as their engines. So it didn't happen. And about 8 years ago, one of the students, a guy named Tom Vaught, who became the director of forced induction at Ford Motor Company, sent me a dyno sheet. Twin turbo V6. Turns out that was the EcoBoost. And of course he rawhided me because it was about 100 horsepower more than we did with the production engine at Buick with a 3.8. But think how it is to go 30 some years and finally see your dream come true. So what I do? I went out and bought an EcoBoost Mustang with a 2.3 4-banger in it. And I'm going to turbo the living shit out of that thing. Thank you all.
Thank you very much. Thank you.